Alright, in this problem we have this spool. It has an inner and an outer radius. So this inner radius has a rope connected to it that is being pulled up at 100 newtons. This outer radius has this rope that's connected to this support. So this rope right here, as we pull this 100 newton rope up, the entire spool sort of rolls along this cord right here. So what we're trying to do is we're trying to figure out the angular acceleration of the spool. And how do we do that? Well, first let's draw a free body diagram, try to figure out what's going on. When we draw a free body diagram, we're going to have this 100 Newton force on the inner spool. On this outer radius, we're going to have this tension force. And right here, through our center of gravity, we're going to have our weight. And this is going to be equal to our accelerations. And we also want to identify our moment of inertia. So when we pull with this 100 Newton force, this spool will move up in the vertical direction, only in the vertical direction. So right here, our mass is going to be 8, and our acceleration, we can just call this the acceleration of our center of gravity. And while we do this, this is also going to rotate. So we're going to have a moment of inertia that rotates in this direction. So our moment of inertia about point G, our center of mass, times alpha. And this is our positive direction. So if we identify our positive directions, there's no forces that acts in this x direction. So we only have this positive direction of y, and we're going to have this this is going to be our positive direction of our moment of our angular acceleration. So these are our two positive directions we're dealing with. So now we can sum our forces in our y and sum our moments about this center point G right here, and use the equations we have for that. So if we sum our forces about y, we get it's our sum of our forces are equal to a mass times an acceleration of G in the y direction. So our sum of the forces on y, which is positive up, is equal to 100 plus t minus w. And w is going to be equal to 8 times 9.81. And this is going to be equal to 78.48. And it's going to be equal to a mass, which we know is 8 times our acceleration of g. And again, we know this acceleration of g is only in the y direction. So since we have no forces in the x direction, we have no acceleration in the x direction, we can ignore our equation for the sum of the forces in the x directions. It doesn't do anything. We're going to get it's equal to 0. There are no forces in the x direction. So we do need to deal with the sum of the moments. So the sum of the moments about point G are equal to the moment of inertia about point G, which is point G is the center of mass, times alpha. And from our free body diagrams, it's easy to see what moments we have to consider. Well, this weight goes directly through our point G, so it's not going to contribute a moment. Put on our positive direction. This 100 Newton force and this T, this tension force of the rope, are going to create a moment. And this T, if we rotate it this direction, this 100 Newton force, if we rotate it clockwise, is going to be a positive because the arrowhead is going to want to rotate first. So we're going to have 100 times this perpendicular distance, which is the radius of point 2. And now we have to deal with this tension force. So we're going to have this T. As we rotate it clockwise, it's going to want to go tail first. So it's going to be a minus T times the outer radius, which is 0.5. is equal to our moment of inertia. Since we're given this radius of gyration, our moment of inertia is going to be m, our mass, so 8 times 0.35 squared. And it's going to be equal to alpha. And alpha is our angular acceleration. Now we have a little bit of a problem. We have an unknown of acceleration of g. We have this unknown of t. We have this unknown of t. And we have this unknown alpha. We have three unknowns, 2 equations. Well, that's okay. We said to assume it rolls without slipping. Now, because we said to assume it rolls without slipping, we can use this next equation. We can use that the acceleration of g is equal to alpha times r. And this r that we use is this long, this outer radius, because this is what it looks like. This cylinder, or this spool, is rotating without slipping on. It looks like it's moving along this cord without slipping. So if the cord happened to be connected to this inner radius, we would use the inner radius. But since this cord is on the outer radius, we're going to use 0.5. So our acceleration of g right here is equal to alpha times 0.5. Now we can just sort of put this back into this equation. So we get 100 plus t minus 78.48 is equal to 0.5 times alpha. So 4 alpha, and this 4 is because it's 0.5 times 8. Now we can, since we want to figure out what alpha is, we can solve for t. So we get t is equal to minus 100 plus 78.48 plus this 4 alpha. And we can take this entire expression right here, this entire expression for t, and we can substitute it in for this t expression right here. And when we do that, I'm not going to write this out, but the only variable in this equation will be this alpha. So we'll have an alpha here and an alpha here. Now we can solve for alpha when we plug in t to this part of the equation, and we can get that alpha is equal to 10.3 radians per second. Because it's positive, it's going in our positive convention, so it's going like that, and that radians per second squared. And this is telling us what our angular acceleration is. Our angular acceleration is 10.3 radians per second squared.